Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 34, we continue with decision trees, and this is the second part of the lecture. So, the concepts that will be covered in this lecture are on CART, classification and regression trees, CART splitting, evaluation metrics in classification, feature importance, and then we will give two examples. One is decision tree for classification and decision tree for regression. So, CART is one of the algorithms using which decision trees are built, and it's one of the most widely used decision tree framework. It was proposed by Bremen et al. In 1984, and this is where we have binary splits only. That is, we can only have two child nodes per split. So that's different from other algorithms. So it supports both classification and regression, and in this particular case, particularly for classification, we use Gini impurity, and for regression we use MSE or variance reduction as the way to decide on which features should be selected. So for classification, Gini impurity measures how mixed a node is, and similar to last we were doing in case of normal decision trees, we were looking into the entropy and then the information gain same way. If a node is pure, all yes or all no, then Gini is equal to 0. If classes are evenly mixed, Gini value would be higher, and CART chooses splits that reduce Gini the most. So that means we will maximize the decrease in Gini. So it's same way we were doing information gain, or we were working with entropy earlier. So it's this CART algorithm supports pruning to balance accuracy versus tree size. In case of regression, the same algorithm will be will do the work in a little bit different way. It predicts a continuous numerical value at the leaf node, and MSE, average squared difference between actual values and predicted values, would be taken, and variance reduction is the splitting criteria. That means after the split, if there is reduction in variance, then only it would be considered. The split that produces the maximum variance reduction is selected. That means which feature will be selected depends on which produce the maximum variance or MSE in that particular case. So now in CART algorithm, there are several hyperparameters, or there are certain parameters which are given using which we can tune the structure of the model. We can control overfitting, we can improve generalization, and so we can also call it one form. We can also control pruning using this tuning of these hyperparameters. So one hyperparameter is the max depth, that is should be the tree depth. We can put a limit to it. Then minimum sample split, that is, we can decide that for samples to be splitted further, there has to be a minimum number. Then minimum sample leaf, that means for the number of samples required in a leaf node, that is, should the leaf node only have one sample or more than one sample, then how many more. Then maximum features, that how many number of features could be considered in each split. That means there could be 20 features, I may not consider all of them in each split, right? And then CCP underscore alpha, this is the cost complexity pruning strength, or higher value indicates more pruning. So as we have discussed in the previous lecture also, that we can prune decision trees when we are using the CART algorithm, and this is the parameter which we can change to decide that what kind of pruning or how much of pruning we will go. So both entropy calculation and Gini impurity help to determine good split points for root or decision nodes, right, for both classification and regression trees. So similar to entropy calculation, we can also use Gini impurity to measure the same. So for a node with class proportions P1, P2 till Pk, so these are the final classes, then Gini equal to 1 minus k equal to 1 to k summation, then probability pk and 2 whole square. We take a square of that, right? So of course, if the classes are only 2, as in CART we know in higher, there are only 2 classes, yes and no. In that case, in case of binary case yes or no, the value would be 1 minus p yes square and p no square. The number of yeses and number of probability of yeses and no and the square. So higher Gini indicates higher impurity and more uncertainty. So pk is the proportion of the samples that belongs to class C for a particular node. And to give you an example, if the node has got 8 yeses and 2 no's, so p yes is 0.8, p no is 0.2, and Gini value is 1 minus 0.8 square plus 0.2 square, which comes to around 0.32. So Gini of equal to 0 indicates the node is pure, that is either everything is yes and no, that is what we want in the leaf nodes. Gini is maximum 0.5, same as entropy, which indicates classes are evenly mixed, 50% yes, 50% no. Lower Gini is less impurity and it's a better choice for a node. So when we use Gini to split, at each decision node, candidate splits are evaluated for each feature one at a time, same as entropy. The weighted Gini impurity after each split is computed, again same as entropy, where we weighted the split entropy after split, whatever was the entropy. Here also after split, whatever would be the Gini value, that we will weight using its proportion. And then the split that produces the largest reduction is in impurity is selected as the root node or the decision node. So because there are only 2 sides to it, that is 2 decisions, that is either left or right, so all split results in 2 child nodes either in the left and right, and so the notation is over here, j is either left or right, and we sum it up, and then nj by n is that proportion, and Gini value is calculated for each of this particular split. I mean that for each of this split, for jth split, for each side either left or right. So instead of Gini, we can also, if we want to do regression, instead of finding the right class, then we can use variance or MSE in this case. So as you know, at each decision node, the candidate splits are evaluated for variance reduction or MSE, average squared difference between actual and predicted values for each feature. So that means once I use a particular feature, after the the prediction happens, there are correct and wrong results, and we can use those actual and predicted values to determine that okay, what is the improvement, considering that if there was no questions that was asked, we started with the the parent node. In the above node, after that I'm asking question, and that results in more split. Is the prediction improving or not? That is what we are trying to decide. So same way, instead of Gini, we are taking variance, but we are taking the same proportion of the left side and right side, and we are taking a summation of that and subtracting it from the upper level, that is the variance of the parent level, and that will indicate variance reduction. So the split that produces the maximum variance or MSE reduction is selected, and instead of MSE we can also go for instead of variance we can also go for MSE as well. So MSE is calculated like 1 by n, 1 equal to summation 1 to n, then yi minus y bar whole square. So this is predicted and actual, and then also we can use this one as well. So we are using the same data set as earlier. We have 14 yeses, we have 9 yeses and 5 nos, total 14. Again, we are trying to determine in this kind of situation where we know the weather, temperature, humidity, wind, will I choose to drive bicycle or not, right? So this we are again trying to determine which are the parent nodes at the beginning. So obviously before we do that, we have to find the parent, the Gini, the impurity value for the before we even start splitting, right? So that is where we know the parent node class probabilities are 9 by 14 and 5 by 14, because 9 yeses and 5 nos. And so when I put it in the formula, 1 minus 0.64 square plus 36 square, it comes to around 0.46. Now, candidate first, again we have to split as per, for the root node first, and we take into account first we take weather, then we take humidity, then we take wind and temperature, and within weather we have got sunny, overcast, rain. Within weather we have got sunny as could be a result, or overcast or rain. So if it is sunny, then the split is between yeses and no is +2 and -3, that is 2 yeses and 3 no's. For overcast it is 4 and 0, that is 4 yeses and 0 no's. For rain it is 3 plus, that is 3 yeses and 2 no's. And in same way, when I do the calculations of the Gini for sunny, Gini for overcast, this is what I am getting, 1 minus 0.4 square plus 6 square, which comes to 0.48. Then because this is perfect split 4 and 0, so we are getting a Gini value of 0. Then Gini of rain is also coming as 0.48. So the weighted Gini is again proportion multiplied by that particular Gini value. And so when we add all those things up, it comes to around 0.343. So the Gini reduction for weather is 0.46 minus 0.343 is 0.117. Same way, if I calculate for Gini reduction for humidity, this one, or wind or temperature, these are the values I get, and we can understand that weather yields the maximum reduction as selected as the root node. So you see the exact same process we are following, and it will result in more or less the same split that is happening in the earlier case. So I am not going to explain that further. For the subsequent steps, you can proceed further, because now we know what is the root node. After I have the root node, I will have my splits, and then again I can choose which would be the right question to ask, right? Same as the you can go to the previous lecture once more, we will follow exact similar steps as we have taken in entropy calculation, information gain calculation. Now, before I move on to giving you examples of Python programs, I want to discuss something more, that this is fundamental to machine learning. It is not only for decision trees, but of course it is how we measure, evaluate the matrices of classification. That means how good the classification is. So it could be applied to decision trees or many other machine learning models. So what we are showing here is the different evaluation metrics we use, and in machine learning classification, as we know, a classifier model or a function is that which maps or predicts unlabeled instances to classes, that is yeses or nos. If it's a binary split, or it could be multi-class split, it could be multiple classes. So that means we have to see that after we have trained the model, we need to see that how good that model is, right? We need to see the predictions made by the model, how good that is, right? So evaluation metrics help us to assess how well the model generalizes to unseen data. That means, of course, the model is built on a set of data, it will be able to predict that data, but if I apply the model in something else, some other data, how good it will be able to predict, and rather in any other sorts of unknown data, how the model results would be consistent. That means how we can generalize that particular model. So various metrics measure different aspects of performance. There are different ways to measure that. The most important one is the one called accuracy. Now, accuracy measures the overall proportion of correct predictions made by a classifier. So that means total number of correct prediction divided by total number of predictions. That's simple. That means out of so many predictions, how many are correctly predicted. So this provides a general measure of how well the model performs across all classes, regardless of how well it handles each class individually, because it tells me that how totally how good is the model. That means we will take each class, how good each one of this is predicted, and we are summing them all up, right? But sometimes it may be misleading. So in case the data set is imbalanced, that means we have got many values from one class and few values of another class. So we may see that all the values of that main class, that is the one which is more, is predicted correctly, whereas all the values of the other class, which is very less, is predicted wrongly. But still it will give us high accuracy score because we are combining them, right? So that is one problem that we have got. So that requires us to look into other matrices as well, right? So this kind of measure is appropriate when class distribution is roughly balanced and when false positives and false negatives are equally important. Now, what is a false positive and what is a false negative? You can see from here, this is a confusion matrix which we will again explain in detail. So, what it does is, on this side we have the actual classes, on this side we have the predicted classes, and this side we are predicting, it could be positive, negative, it could be male, female, it could be any zeros, ones, anything, right? So, these are positive ones and these are predicted as positive ones, right? So, these are called as true positives, right? Let us assume there is 42 of those. And then this is a positive one but predicted as a negative one. So, that means it is false negative. So, it is not actually a negative but predicted as negative. So, there is 8 of those. Then this is negative, that negative, or this is male or this is female. So, it is how many of them are predicted as positive or male. So, that is false positive. This is 18 of them. And how many of them are truly predicted as negative? That is, this is negative also predicted as negative, or this is female also predicted as female. So, this is 32. So, this is known as true negative. So, confusion matrix shows a table of prediction outcomes comparing actual versus predicted classes, and over here if you calculate the accuracy value is 42 plus 32. These are the true positive and the true negative. These are the correct predictions divided by all the other predictions, which comes to around 0.72. So, that means for 70% of the cases it is predicted correctly. Now, the question is, this as we have discussed, so there could be many other things that we need to find out. So, to generalize, instead of taking male, female or something, we can say that this is actual yes, actual no, or predicted yes, predicted no, and we can say true positive, false positive, and accuracy could be given using this particular formula. So, TP is correctly predicted positives, TN is correctly predicted negatives, FP is predicted yes but actually no, predicted no but actually yes. So, unlike accuracy, what happens is instead of, if I don't do, accuracy could be measured like this, but I can just measure accuracy without even doing this kind of a confusion matrix, right? I can just calculate the total number of positives, and then I can say that what is the accuracy of that particular prediction. But unlike accuracy, if I divide the data into this particular way, it reveals the different type of errors, that is how many are false positives and so on. So, it forms the basis for some other matrices like precision, recall and F1 score. Now, what is precision? Precision, the full form is positive predictive value. So, precision measures the proportion of correct positive predictions, that is true positives, out of all instances that the model classified as positive, that is both true positives and false positives. So, you see precision is TP divided by TP plus FP. So, what it says? It says that high precision means that the model makes fewer false positive errors. That means it doesn't incorrectly label negative instances as positive. Now, this has got very high connotations. So, why it is important? It is important when cost of a false positive is very high. That means I incorrectly label a legitimate bank yield transaction as a fraudulent, and I start an investigation on it, right? So, this could be costly. So, that is why false positive, if it is the cost of that is very high, then I have to make sure that the number of that is less. So, that is where the precision matrix helps. Then there is something, the next matrix is recall, which is sensitivity or true positive rate. Recall measures the proportion of actual positives, true positives, that were correctly identified by a model out of all the actual positive instances that are there. That there could be true positives and false positives as well. That is, out of all the yeses, how many are correct yeses, right? So, that comes as TP divided by TP plus FN. So, recall is important when the cost of a false negative is high. For example, in dengue detection, where missing an actual positive case could have severe consequences, right? So, recall is important that way, right? So, then comes F1 score, which actually combines both precision and recall. So, what it takes is it's a measure which balances precision and recall to evaluate overall class performance, and we take a harmonic mean of both precision and recall, as you can see over here, and this actually balances both the types of errors, and it is useful for also imbalanced data sets. That means where you see data sets skewed towards certain classes, this actually is, it is used. In addition to that, we have some other measures. One is called support. It indicates the number of true samples per class, explaining how much each class influences accuracy and other evaluation matrices. So that means it tells us what are the true samples per class, true predictions per class, right? Then using support, we can also have, and also using precision recall F1 score, we also can create some macro averages, which calculates the metric separately for each class and then takes their simple average. So either you can calculate these matrices and then take an average of those. And for weighted average, what we do is we can use support, not for macro, we don't use support for macro averages, but weighted average is we compute the class-wise metrics and average them using class support as weights. So these are different ways to measure the accuracy of the model or the predictions of the model that we built. So in addition to checking the accuracy of a model for this kind of classification task, because decision tree is the first classification model that we are learning, so there is another important thing that we need to understand, that is what is feature importance, right? So that means which input variables actually influence the model's decisions. That means not all variables are important. So whenever we are building a model, we are trying to find out that which are the major features which are playing a role in the decision for a person to choose bicycle or not, right? So feature importance help us in interpreting the model, and we can determine which policy, planning and infrastructure decision can actually change my choice, right? Which things I need to improve, which things I need to change, so that will impact my choice. So that's why this finding the importance features is very, very important. So prediction is one part of the task. That is, when I'm developing a model, one job is to do the right predictions. The other job is to find out which parameters or which features play a more dominant role in my choice, right? So that is why we have to determine feature importance. So it reveal as well as validate domain insight or theory. So whenever we are building a model, we have discussed earlier that we start with a theory or some hypothesis. So this feature importance actually confirms that if we are right, or sometimes it also helps us to reveal some new features which are actually playing a role. So it helps in determining unimportant features to find the right tree depth. So that means if I understand which are the important features, I can remove the ones which are unimportant, and that will not affect my decision or the results of the model that much, right? So this is actually good, and it helps in preventing underfitting and overfitting, thus simplifying model and reducing noise. So unexpected features may indicate data leakage, encoding issues or bias in data. So sometimes we find some feature becoming very important, but I know theoretically that it has not too much influence on the final outcome. So in that case, there may be some problem in the data, right? So that also is an indicator. So that's why we always do feature importance, right? Then looking into other aspects of decision trees or CART in general, in particular. So that is the depth sensitivity. That is the predictive performance depends as the maximum depth of the trees changed. So that means we can work with different depths and see which one is giving us good predictions. So multiple decision trees are trained using different values of the max depth parameter, and their performance is compared. If the depth is too small, that means sometimes important patterns are missed, they are non-captured, so this is underfitting. And if the depth is too high, then the model very easily fits to this particular data, but it may not fit to other data. So that leads to other problems, which is overfitting. And then of course there is the pruning task. That is, sometimes we can if a tree is overgrown, then we can prune it. And then first we grow the tree, and then we decide that how to prune it. And we can systematically remove branches that do not provide sufficient reduction in prediction error. And in this CART algorithm, we use CCP alpha parameter, which actually takes care of that. So strength of pruning could be increased by penalizing by model complexity. And so this is the strength of pruning. So the more model is more complex, then we need to carry on pruning. and the optimal value of what should be the right value based on model performance. We can test, we can use the predictions, we can test it on we can run the model on test data, and then we can accordingly take a decision on what should be the right parameter. Now coming to examples, we will do two examples very quickly on classification task and regression task. More or less it's same, only little difference is there. So here we are importing from pandas, PD, matplotlib, PLT. Then we are using sklearn to import train test split. Then we are importing one-hot encoder and level encoder. Of course, we are doing it because we have got categorical variables. And then column transformer we are bringing in. Then the pipeline we are importing so that we can build a pipeline here, and we will explain what's a pipeline. And then we are bringing the actual model, that is the decision tree classifier, and then we can also plot the tree as well. So that means this is a special module which help us to plot the tree. So from and also we can bring in accuracy score, confusion matrix, classification report. So this would be help us in understanding the model matrices or how good the model is. So we load the drive bicycle underscore 3x, that same data sets that I was displaying. pd.read underscore csv actually loads the data in the data frame, and we can print that shape of the data frame, we can print the top 5 rows, and then if there are missing values I can also remove them, right? I can print them, and if those are not there, then we can also we can count them, whichever things are missing, and then we can also, in case there are something missing, we can replace them, those rows and so on. So for that is what we are doing. So this is the data shape for, so we are printing data shape, this is what is coming, 42 and 6, and then we are taking this first 5 rows, which is, this is the data that we are getting over here. We are printing that, we are getting 0 values for missing values, so everything is there, and the class distribution is also given, that is how many of yes and how many is no, and that actually happens over class distribution over here. Yes, value of we are taking this one. And then we are storing the x and y values, that is what is the predictor and what are the features. So x is the features, so weather, temperature, humidity, wind, we are storing it in x, and y is the the one that we are predicting, which is drive bicycle, and so this is the target y and the features x. So then we are calling the level encoders to transform the data. So that means we can transform this drive bicycles to 1 and 0. This is the target variable, so that is what we are doing over here. And then what we are doing is we are then calling the train test split function, and we are storing the output in train test, y train and test. We are just splitting the data into train and test part. 30% of the data is kept as for testing, and the rest 70% is used for training. Random state is 42, which ensures that we again and again we do the same split, and stratify equal to y encoded means we make sure that the yes no will be similar both in the train and the test split. Then we store the features in the category columns, and then this particular variable, and then we do the pre-processing, that is we call the column transformer, and then within that we can run the hot encoder, and we are storing the values, and whatever is there in cat columns we are storing it in this transformers. So that means we are converting it and using one hot encoder into dummy variables, and we are then storing it over here. And then the drop actually says that the columns not mentioned in the transformer list will be dropped, and ignore somewhere is over here. It ensures that model do not crash in case of new category, and it will convert everything to 0. That means if it is not, it finds a new category there, it will convert it to 0. And then once we have done that, then we are calling the decision tree classifier, and that is the results will be stored in cart. The criteria is Gini. So this is where we are measuring the criteria. Maximum depth is 3, but we can always adjust that. And then minimum sample leaves should be 1, and then random state would be 42. So this is the cart model or decision tree, and we are using Gini impurity to find the results. So then we are building the model pipeline. So the pipeline is basically where we are, combining the steps of pre-processing as well as, the model itself. That means which model we are utilizing. So what happens is every time I run this with a set of data, we can just call the pipeline and it will, follow the same steps. We don't have to repeat writing it again and again. And then once we have done that, we are fitting the model. And then once we are fitting the model, then model fit is xtrain and ytrain. Ypred is model dot predict of xtest. We can predict the results for the test data, and then we can print the accuracy score. So first we print the accuracy score based on ytest and ypred data. So ytest is the actual data and ypred is the once the model predicts, that is the data that we are comparing, and then from there I can check what is the accuracy levels. So this is the two things that we have to pass into this particular function. Then similarly for confusion matrix also I pass on ytest and ypred, and for classification report I pass on ytest and ypred, and then we give target names y encoder classes, and this that means it will show us that particular whatever has been encoded, those classes will be shown over here. And once we have done that, then we can see this kind of a result. Accuracy value comes around, so we are printing all these three, so accuracy value comes around 0.53. Confusion matrix you can see 5602. This is true positive, true negative, then false positive, false negative, and so on. And this is the classification report for each of the classes, yes and no classes. What is the precision value, what is the recall value, what is the F1 value, what is the support value, and so on. So overall accuracy is even given, macro average, weighted average, both are given. And then once we are done with it, we also need to understand the feature importance, right? And to do the feature importance, what we do is we look into the feature importance function and we store it, and then what we do is we, along with the feature names and the feature importance, that is whatever we are storing here, this feature is getting stored here, we can print it together in a this particular variable or list, you can say. Then this we are printing one after another. We are printing this 12 features, this data frame we are printing, and this actually prints like 12 of the features. It could be depending on what we are choosing, right? So the features are humidity normal, weather overcast, weather rain. Each one is chosen. It is not like humidity. Humidity has got three classes, so the feature becomes humidity normal, humidity overcast, and what humidity high, and so on. So we see that humidity normal, weather overcast, weather rain, these are the sequence of the feature importance, which are the most important factors which has played a role in deciding that this feature should be included in the model or not. If it is 0, most likely these are very unimportant features and could be removed from the model. So once we have done all this, we can also plot the tree. For that we are using plot tree function, and these are the different things that we have to put in, what are the feature names, and then some that rounded is equal to 2. So that means it converts encoded, then this encoder classes allows converts encoded levels to no and yes. So this is a standard way we do that. And then we can also print the title of the decision tree, this particular plot, car decision tree genie, drive bicycle, which is from CSV. So this entire thing has been printed. So once I have created the plot tree, then I can show that with the plot.show function, and this is how it looks like. So plot tree function is a utility from sklearn tree which draws the structure of the trained decision tree. So over here you can see that because it's not the what we have did earlier, so there is difference of this decision tree from the one we developed earlier. So this is based on the CART algorithm, where it's a binary classifier, and binary classifier uses this point it is either lesser than 0.5 means it is yes or no, right? So it is no. So in that way we go, right? So either in yes, then it goes in one direction. If it is no, it goes in another direction. So that is what it specifies. For each level, how many samples are there? What is the Gini value of that particular level? And the yeses and nos all are given as well. So humidity and weather conditions dominate bicycle usage decisions, while temperature and wind plays a minor role in this CART model. and 0 importance does not mean the feature is irrelevant, just it was not selected by this specific tree, as we have seen in the importance feature. So that is what it shows here. That means weather overcast, yes or no, humidity normal, weather rain, and then weather. So these are the ones which are chosen for deciding, the split in this particular model. So the plot shows the sequence of decision rules. Each internal node shows a binary split condition, the Gini impurity, number of samples, class counts, no ODS, and each leaf node shows the final predicted class. That is, yes, this is the final predicted class as well. Okay, so these are the leaf nodes. So this is again the leaf node, right? So so this is how we develop the classification tree. Same to that, we also can develop the regression tree. Same data set we have used, it's a little bit longer than the one we used to give an example in the last lecture. It is having more number of rows of data, and here instead of we do more or less everything remains same, and the matrix that we use is the mean squared error instead of all the accuracy and all these things we did over there, and the mean absolute error R square score is also utilized. So we load the path, same file we load in the data frame, and then we load that particular path, and then we load it in a data frame, and then we can see the shape of that data. We can print the first 5 rows, and then also we can print the missing values if there are any, and their count. This actually helps us to determine the number of missing values, so there is none. And then we can also map the yeses and nos, how many of those are there, and then x and y value, the target and the feature values are being loaded over here, and then we can also print the summary statistics of this data set, right? So what is the summary statistic? It gives us the total count, how many rows are there, what is the mean value, what is the standard deviation, what is the minimum value, and all this the percentile values and the maximum value. Now what it does is, what we have done over here is, instead of having yes and no's, we have done we have put a value for that. Yes has become 120 and no has become 40. So actually there is no value. It is not a continuous thing that we are printing, but the algorithm, if you give a continuous code, it would be able to categorize, is it near to 120 or is it near to 20. It would be either predicting 120 or it would be predicting 40, right? So we just replace that with continuous variable, and we are doing it. So I could have used another case where there could be more classes, more number of values would be there, but for simplicity we have assumed 120 and 40 for yes and no's. So that makes them continuous, and that makes them a regression model. So same way we are training them or splitting the data, then we are using column transformers, we are using monohot encoder, we are encoding the values, and then we are calling the decision tree function where the criterion is squared error instead of Gini, and max depth is 3, random state is 42, and finally we can we have the pipeline here, and then we can fit the model, and once we have fit the model, we can predict use for X test, the test part. So after training, this is the test data for which we are predicting, and once we have predicted, we can predict the mean squared error, and we can predict the root mean square error. We are taking a root of that. Then we are print the MAE mean absolute error. Then we can print the R square values between Y test and Y pred. So all these things we can do, and as you can see, these are the results that are coming. So you can see the MSE value, the R square value is 0.63, MAE value is 12, RMSE is 22, and so on. Now here also we can find the feature importance the same way we did earlier. So we again see which are the categories for the different columns of different features, important features. Using this function, we can print both the feature names as well as their importances, and we get the feature names first from the category columns, and then we can print them, and at the same point of time we are also getting their importance as well. So this is the list of features. Again we can see winds, weather sunny, humidity high, weather rain, wind weak, These are the ones which are important, but the other is not having any relevance at all. So here also I can build the plot. Same way we are done earlier. We are printing the cart regression tree, and this is how it looks like. Here also the decision is there, but instead here we are getting values at the end. So that means regression leaf shows the mean target value in that particular leaf node. So the regression tree plot shows the squared error, this number of samples, and the value which is the predicted mean, which is given in each of these cases. So this is the references that we have used. And to conclude, CART combines simple decision rules with rigorous evaluation and pruning to deliver interpretable and effective supervised learning models. Thank you.